Hey everybody, I hope you're all doing well. This video is a continuation of looking into how to use TensorFlow in Scala. This video is going to focus on implicit construction of tensor values and a bit on the shape of tensors. Like in the last video, I'm going to be doing this in the Ammonite REPL. I'm going to be using a pre-def that loads in TensorFlow, along with adding a pretty printer for tensor. I'll include a link to this pre-def in the video description below. Back in the terminal here, we're going to take a look at that pre-def. In particular, I want to highlight this import. This imports the API package object. This is the API package object. You don't have to import this API package. You can import the individual pieces, but I think it's a pretty good prelude. I haven't had many issues with conflicts, even with the implicits. And just browsing through this, we can see there is quite a few types that are going to be introduced, quite a few implicits. And the ones we're going to cover initially are the implicit conversions from various types to tensors. Back at the terminal, I've loaded up Ammonite. Consider this array. This is an array of integer elements of size 2. Now consider this one. Like the previous one, this is an integer element array. However, this has a size 4. Considering this one versus the first array, this array has a size 2. Each element, though, is an array. Those arrays have a size 2. Similar to the prior array, though, the data contained within this array is the scalar values 1, 2, 3, 4. There are only 4 scalar values for both of these arrays. Further examples to consider. This array, like the previous two, contains the 4 scalar values 1, 2, 3, 4. This one has the same number of dimensions as this prior example. However, the first dimension, or the first array, has a size 4, while the first array here has a size 2. The second array has a size 2 here, while the second array has a size 1 here. As a final example, this array, like the very first one we considered, is a size 2. However, the values contained within it are booleans. In all of these cases, we could imagine doing operations on every single element of the array. For instance, for this first one, we could imagine adding 1 to every element. Then a map of +1 would do exactly that. Likewise, we could imagine adding 1 to this array, where the same function would work just fine. However, when we get to these later arrays, we could also imagine adding 1 to every scalar value. This map, however, won't work because we are trying to add 1 to an array of int, which is nonsensical. There are 2 more points to keep in mind before we move on to tensors themselves. One is that we have this one-dimensional array. So what is a zero-dimensional array? That means that there are no indices required to index the scalar data. That would be a scalar value itself, such as just 1. So 1 we can consider a zero-dimensional array, then we have one-dimensional array, two-dimensional array, three-dimensional array. The last thing to cover is the type of tensor in Scala, and that is a parameterized type that would look something like this. So we know that x here would be a tensor of the data type float. This tensor value could be a singular scalar or a multidimensional array of scalar value. We're first going to start by introducing zero-dimensional scalar tensors. And we do that with implicit conversions from those scalar values themselves. And here we've constructed a tensor T0 of type tensor of int from the scalar value 1. And we see in the summary that it prints us out a bit more information about the tensor than just the type. We get the type and this notation here. This notation describes the shape of the tensor. Recall back to our prior examples of multidimensional arrays of integer values. Those would also be a tensor of type int. And we could also introduce a tensor of type int from a multidimensional value. And here we see that the type again is tensor of type int. However, the notation for the shape is different. Now it has a integer value in there, and that value is 2. This notation means T1 is a one-dimensional tensor of size 2, which does follow from it being constructed from a one-dimensional array. Let's do another scalar tensor. And in this case, T2 is a tensor of double with the scalar value 1.0. In the case that a tensor is a scalar, we can get back out that scalar value by using the method scalar. If a tensor is a multidimensional array of scalar values, there is a entries iterator. This also works for scalar values. Let's try a few other examples. Tensor of int. And then here is a tensor of double that I've constructed from an int. Within the implicits for TensorFlow, there are conversions from tensors of ints to tensors of doubles, which is what's happening here. First, a tensor of int is constructed, which is then converted to a tensor of double. If we were to try the other direction of going from a tensor of double to a tensor of int, namely trying to construct a tensor of int from a double value, this wouldn't compile. Let's try one other example. We can also construct tensors of strings and consider those strings scalar values. There are 3 useful properties to examine tensors: shape, rank, and size. Each of these is a scalar tensor. The rank is 0, the size is 1, and the shape has no dimensions, as we can see here. Rank and size can be determined from shape. And when you print the summary of a tensor, you see that it only includes shape. Still, rank and size can be useful on their own. There is one other useful property of tensors, and that is the data type. Recapping a bit, we found that we can take our scalar values and treat them as tensors implicitly. Specifically, these are tensors of rank 0, size 1, and this shape. Now let's look at a few more examples just to get a hang of this. These are all implicit conversions from scalar values to scalar tensors. Let's go back to our multidimensional array example. Similar to treating scalar values as scalar tensors, we can treat multidimensional arrays as tensors. I've constructed 3 tensors from arrays of different shapes and dimension. T1 is a one-dimensional array of 4 elements. T2 is a one-dimensional array of 2 elements, while T3 is a two-dimensional array where the last dimension has 2 elements and the first dimension also has 2 elements. And we can see here in our shape from the summary, something that looks about the same as what I described as the size of each dimension. And that is indeed what the shape is, the size of each dimension. We can ask what the ranks are for each of these. And we note that T1 has a rank of 1, T2 has a rank of 1 also, while T3 has a rank of 2. Recall that our tensors from just scalar values have a rank of 0. And we see that rank corresponds to the number of dimensions in our shape. T1 has a rank of 1, and there's 1 dimension in our shape. T3 has a rank of 2, and there are 2 dimensions in our shape. We can query T1, T2, T3 for shape directly. And we see T1 has a shape of 1 dimension of size 4. T2 has a shape of 1 dimension of size 2. And T3 has a shape of 2 dimensions, the first dimension of size 2 and the second dimension of size 2. That's all for this video. I know it's like 10 minutes and we've only covered implicit construction of tensors as well as a bit on shape. The extra time now should hopefully help solidify these ideas, since we'll rely on them a lot later. Next video I'm going to cover some explicit construction of tensors, as well as finally some basic operations on tensors. I hope you have a good rest of your day, and I'll talk to you then.